In this video, I'm going to talk about where complex numbers came from and why they were invented. And I'm going to leave you towards the end with a thought on how there is some similarity between how they were invented and how we use complex numbers today, or how you might use them in this course. This video is not about how to do mathematics with complex numbers. I have a whole bunch of other videos that I have made on that. And this is just about the history of complex numbers, which is actually quite fascinating. And if you use complex numbers, I think it will be very interesting for you to know where they came from. The first time you probably saw complex numbers was when you were trying to solve quadratic equations, right? In the history of mathematics, several cultures had known how to solve quadratic equations many centuries ago. The Babylonians knew how to solve quadratic equations. Indians knew how to solve quadratic equations several centuries back. And in about 800 AD, there was a Persian scholar by the name Al-Khwarizmi, who wrote a very influential book on algebra, which was known to the Europeans in about 800 AD. So by that time, several ways to solve quadratic equations was pretty much known almost everywhere in the world. And when you encountered quadratic equations, you are probably told this formula to find the roots of a quadratic equation, right? It's the famous formula, which is minus b plus or minus square root of b squared minus 4ac over 2a. And sometimes what happens when you try to use this formula is that the b squared minus 4ac inside the square root, which is called the discriminant, sometimes becomes sometimes becomes negative, right? When it becomes negative, you're forced to take the square root of a negative number. And there is a misconception that complex numbers came because you wanted to take square roots of negative numbers when trying to solve a quadratic equation. So for example, if the quadratic equation is x squared minus 2x plus 5 equal to 0, then when you compute b squared minus 4 times a times c, you notice that it's negative 16. However, complex numbers did not come when people were trying to solve quadratic equations. Now notice that the solution to this quadratic equation, x squared minus 2x plus 5, is 1 plus 2j and 1 minus 2j, and both of them are complex. And in fact, they are complex conjugates of each other. In other words, if a quadratic equation has complex roots, both the roots are complex. And people were not really interested in quadratic equations that have complex roots because these equations didn't really have much physical meaning. So they didn't think these equations were interesting, and they didn't really have a need to try to invent square roots of negative numbers when dealing with quadratic equations. However, the cubic is quite interesting. So even though by 800 AD we knew how to solve quadratic equations in most parts of the world, it took more than 700 years for people to find a formula for the solution to a cubic. So a general cubic is an equation of the form a times x cubed plus bx squared plus cx plus d equal to 0. And between 800 AD and 1520s, people were trying to find a formula, just like the quadratic formula, to find a solution to the cubic. And this eluded people for 700 years. And in fact, in the late 1400s, this was considered a big challenge in Italy to be able to find a solution to these cubic equations. Now, you might be wondering, what does complex numbers have to do with cubic equations? And here is where the story starts. So it turns out that there was a mathematician by the name Scipione del Ferro. So Scipione del Ferro found a formula to solve a particular form of the cubic equation known as the depressed cubic. So he found a solution, a formula to solve cubic equations of the form ax cubed plus bx plus c equal to 0. Notice that the x squared term is missing there, and this is called as a depressed cubic. However, he did not really reveal the solution to the world. And you might be wondering, why would a person who found a solution to an important mathematics problem did not tell anyone about this? And to understand that, we have to go back to medieval Europe. And in Italy, if you're a professor of mathematics, you can be challenged to a mathematics competition. And if you lost in the competition, you could potentially lose your job. So many mathematicians who invented new solutions usually held out these techniques so that they could counter-challenge someone if it ever came down to having to respond to a challenge. So Scipione del Ferro did not reveal this solution, and on his deathbed, he gave the solution to his student Antonio del Fiori. So at this time, so this is early 1500s, Del Fiori has the solution to the depressed cubic. And Del Fiori realizes that since nobody else has the solution to this, he could challenge another mathematician called Fontana, Niccolò Fontana, who is known popularly by the name Tartaglia. And Tartaglia apparently in Italian means person who stammerer or speaks in a stammering way. So when he challenges Tartaglia, it looks like Tartaglia actually knew the solution to a different depressed cubic given by ax cubed plus bx squared plus c. So during the competition, Del Fiori gave 30 mathematical problems to Tartaglia, which were all solutions to the first form of the depressed cubic. And Tartaglia gave solutions to Del Fiori, which were all problems of the second form of the depressed cubic. It turns out that Del Fiori could not solve it, but Tartaglia, on the other hand, during the competition, found a solution to the depressed cubic ax cubed plus bx plus c equal to 0, and he came out with this nice formula that I've written on the screen here. So now word spreads around that Tartaglia had solved solutions to the depressed cubic, and now enters Girolamo Cardano, who was a famous mathematician in Italy. He gets intrigued by the fact that Tartaglia had solved these depressed cubics, and he approaches Tartaglia and asks him for the solution. And Tartaglia refuses to give the solution to him, and Cardano cajoles him for the next 4 or 5 years, and after much effort manages to get the solution from Tartaglia, who gives him the solution in the form of a poem, under the condition that Cardano is not supposed to reveal to anyone. So he takes an oath from Cardano that he's not supposed to reveal the solution to anyone. Cardano promises Tartaglia that he would not reveal the solution. And then Cardano, along with Ferrari, realize that the solution to the depressed cubic can be extended to find the solution to the general cubic. And Cardano wants to publish this solution, but clearly he cannot publish it because he's under oath. And now an interesting turn happens. Since Del Fiori had given Tartaglia these depressed cubic problems, Cardano and Ferrari wanted to know what Del Fiori knew about depressed cubics. So they go to Del Fiori's house and they realize that Del Fiori actually had the solution to the depressed cubic before Tartaglia. And now when they realize this, they take the viewpoint that their oath is no longer valid because Tartaglia was not the first person to find the solution to the depressed cubic. So this clearly angers, and then they go ahead and publish this in a book written by Cardano called Ars Magna, or the Great Art, in 1545. Now, needless to say, this clearly angers Tartaglia, and then Cardano and Tartaglia go through an extended period where they fought with each other. But that's not part of the story. So now you're still wondering, where did complex numbers come from? We're just talking about cubics. So here's where it comes from. So let's think about the solution to x cubed minus 15x minus 4 equal to 0. So Cardano had the formula to solve for this, right? So if you look at this equation, this equation corresponds to a being 1, b being negative 15, and c being negative 4. And if you plug this into Cardano's formula, you get this formula, which involves square roots of negative numbers. Of course, they didn't know what to do. Cardano did not know how to take the square root of negative numbers. In fact, even negative numbers themselves had not been widely accepted until very, very late in the history of humans. So Cardano did not know what to do with the square root of negative numbers. But interestingly, if you look at this cubic, you realize that there is a real root, x equal to 4, for this cubic. So if you plug in x equal to 4, you see that x cubed is 64 minus 15 times x minus 4 is equal to 0. So Cardano knew that eventually he had to get a real number as the answer. However, he was stuck because he had to take the square root of a negative number. And this is where, for the first time, Cardano says, okay, let me assume that there is square root of negative 1. Let me just pretend like I can write square root of negative 121 as 11 times square root of negative 1. And if I do that, he realizes that what is inside this cube root turns out to be the cube of 2 plus square root of negative 1. I mean, you can plug this thing and you can evaluate it, and then you see that 2 plus square root of negative 1 is just 2 plus square root of negative 121 is just 2 plus square root of negative 1 cubed. Or equivalently, the cube root of 2 plus square root of negative 121 is just 2 plus square root of negative 1. In the same way, he realizes that the cube root of 2 plus square root of 2 minus square root of negative 121 is simply 2 minus square root of negative 1. Now something really interesting happens, because when he adds these two terms, the square root of negative ones cancel each other out, and you end up with a real number, which is 4, which is indeed the solution to the cubic. So this was the first time we introduced an idea of square root of negative 1, but notice that this was introduced purely as a way of convenience. You introduce this as an intermediate step in a calculation because you knew that eventually you had to get a real number as your answer. Even though Cardano did this, it made him very uneasy. Cardano never really quite was comfortable with the square roots of negative numbers, but it was really Raphael Bombelli who realized that these things are valuable, and even solutions whose roots are not real are interesting, and he persisted with the idea of square roots of negative numbers and described how to do arithmetic with square root of negative numbers, so on and so forth. And Bombelli is regarded as being the person who really started believing in complex numbers and pushed for their acceptance. Of course, then there were a series of mathematicians who did phenomenal work in complex numbers, including famous names that you see here. So what's the lesson we have to learn from this? So when you take a class in electric circuits or signals and systems, quite often you may face a situation which is very similar to what Cardano had to face in the following sense. So let's look at this electrical engineering problem. So let's say that I have a voltage source V, and let's say that I have a simple RC circuit. I have a resistor, I have a capacitor, but the voltage source is an arbitrary source. And let's say I want to find the current. So this is a function that's changing with time, and I want to find a current in this circuit. Now you know that the current in the circuit is related to the voltage through some differential equation, right? Now one way to find the current is to solve the differential equation. Another way is, a simpler way is typically to use a Laplace transform and relate the Laplace transform of I to the Laplace transform of V, and then take the inverse Laplace transform of I in the end. And you will notice typically that the voltage waveform may be a real waveform, the current waveform is also a real waveform, but the Laplace transforms are actually complex quantities. And quite often these complex quantities confuse students. I mean, you can interpret these complex quantities, but the first time you see them, you really don't see the interpretation that easily, and this kind of confuses students as to what these functions are, why you are getting complex values. And the point I want to make is this: sometimes this Laplace transform makes the computation or solution to the differential equation easy. But in the end, the quantity that you are really interested in is really a real quantity. So the current waveform is really a real quantity. So there is nothing complex about the current that you are interested in or the voltage waveform itself, but it's just convenient to go through these complex numbers.